This is 1984 IMO problem number 5, and here is a view of this problem. Let D be the sum of the lengths of all diagonals of a plane convex polygon, so a convex polygon with n vertices. So let's let that polygon be named as A0, A1, A2. These are all the vertices all the way up to an minus 1, a sub n minus 1, and let P be the perimeter of that polygon. Notice that the polygon is not necessarily regular. We need to prove these inequalities, these two inequalities. Let's start from the left-hand inequality. Let's first investigate this side. Before we do that, let's first count the number of diagonals in an n-gon, right? In an n-gon. Well, obviously this is quite simple. That's just equal to well, you have n vertices and you want to choose two of them, right? And you connect them, you get a line segment which can either be a diagonal or a side length. So you want to make sure that it is not a side, one of the n edges. So that's it. That would simply give us n times n minus 1 over 2 minus n, and I can write it as 2n over 2. So n squared minus n squared minus 3n over 2, which is finally 1/2. Factor out the n minus 3. Alternatively, you could have done so each of our vertices, so consider this, this is our convex n-gon. So consider this vertex. This vertex is can be connected to all the other vertices through diagonals, except that, so therefore except that it cannot go to its two neighbors and to itself. So therefore, from each vertex, and we have n vertices obviously, we can go to n minus 3 of the other vertices. However, notice that because I'm multiplying it by n, these are ordered. So to make it unordered, I need to divide it by 2, right? Because I'm double counting each diagonal in that case. But regardless, okay, so you get the same answer. So this is the total number of diagonals of any given n-gon. I want to prove next the following claim, which is, I think it's okay. So what the claim is that so if you have a convex polygon, I don't know, let's do it like that, like that. Okay, so so this is, say, vertex 0, vertex 1, or sorry, I think we decided to call them A0, A1, and let's call this one as A sub j plus 1, and let's call this one A sub k, and this one as A sub k plus 1, and so on. Now the claim is the following. If you consider the diagonal AJ, AK, as well as AJ plus 1, K plus 1, and these two edges, okay, then the claim is that A sub j, A sub k, the length of that diagonal, plus the length of A sub j plus 1, so A sub k plus 1, I claim that this is strictly greater than A sub j plus 1, plus A sub k plus 1, these two side lengths of this n-gon. The proof uses the triangle inequality to observe that. So let's call this intersection point as P, or we can directly establish some length relationships, which I think will make our life easier. So let's call this length as A, this one is B. Let's call the length connecting these two, so forget about this point P, we'll make it easier. So let's call this one as C. Then this diagonal here, or let's start with AJAK. AJAK, let's call it as D, as a diagonal, the whole thing, and this one is E. So formally, we want to show that D plus E is strictly greater than A plus B, right? So equivalently, show D plus E is strictly greater than A plus B. Well, proof. It's quite easy actually. So the main idea is to apply a triangle inequality twice, once in this triangle and once in that triangle. So let's do it. So in that triangle, A sub k plus 1p. Oh well, before we can do so though, we might need to split D and E into two parts. Let's call this one as E1 and this part is E2. Similarly, let's call this one as D1 and this part is D2. So therefore, applying triangle inequality in triangle P A sub k plus 1, we just realize that D1 plus E1 is strictly greater than B. And now applying triangle inequality in triangle A sub j plus 1p, we just realize that D sub 2 plus E sub 2 is strictly greater than A. Now we can add up these inequalities respecting the direction of the inequality. We just realize that D1 plus D2, which is simply D, plus E1 plus E2, which is simply E, is strictly greater than A plus B. So that proves our claim actually. Now we are ready to prove the left-hand side. So this first inequality. So what I will do next is, now that we know this inequality holds, I will go ahead and add this inequality over and over again. How many times? Over all the diagonals AJ, AK. I want this to trace all these n times n minus 3 over 2 diagonals. Okay, so what happens on the left hand side? So if I sum all these left hand, so let's do it here. So therefore the sum over all these 1/2 n times n minus 3 diagonals, I'm adding a sub j, a sub k plus a sub j plus 1, a sub k plus 1. So this is the left hand side, right? So what's going on the left hand side? So let's make note of that. So the left hand side of this inequality in the claim, we're adding over all these diagonals. Hey, we can split the summation sign, a sub j, a sub k, and then adding over all diagonals, all these number of diagonals plus all of these. So this is another length here, and this is also a diagonal length, but we're adding across all the diagonals again. So all that we do is we add all the diagonals twice, right? So does that make sense? But because the sum of this is all the diagonals, the sum of all the diagonals is simply D, and the sum of all the diagonals repeatedly, that's D again. So that's 2D actually. So the left hand side, on the left hand side, we have each diagonal appear 2 times. Now how about the right hand side? What's going on the right hand side? On the right hand side, instead, we have the side lengths. This is a side, this is a side. So for each diagonal, each of these side lengths repeat, right? So the way they will repeat will be the following. Once you draw a diagonal like this, for instance AJAK, so this diagonal, what will happen is we will count this length once, right? And then as we move to the following diagonal, a sub j plus 1, a sub k plus 1, so this will also create this diagonal, nothing will happen. But okay. So but on the previous diagonal, I should have said, so on the previous diagonal, let's say this one, I don't know, so you will have another length here. So for that particular one, we are repeating it again, right? Does that make sense? Or yeah. So therefore we are repeating it twice in that case. So each diagonal, so each edge is repeated twice for each count. Do you see that? So each of these edges will be So this count two separate edges, but because we are cycling, we are summing everything. Like we are making a rotation of a diagonal, right? So the diagonals will keep rotating. So each of these edges will be counted how many times? Does that make sense? Oh, or even better explanation. Check this out. Check this out. Okay. So all right. So from each vertex, so we have our neighbors, right? So we don't want to go to our neighbors. We have all these diagonals, right? So from each vertex, we will have n minus 3 diagonals come out of it, right? 1, 2, 3, 4, and blah blah blah. N minus 3 diagonals. So therefore, when I go to each of these diagonals, I will count any given edge how many times? N minus 3 times, of course. Does that make sense? So, but then I should be careful, because even though I say I counted n minus 3 times, I really need to divide it by 2, because I will do, when I go to that vertex and this one goes to n minus 3 of its neighbors, you see that this one is being repeated. So each diagonal is repeated twice. Okay, so really divide it by 2 now. But wait, all of these edges are counted twice. So this is 2 times the perimeter then, and then when these will just simplify with the 2's will simplify. So it is as if each edge will be counted n minus 3 times. Does that make sense? So therefore, that's it. So therefore, this sum on the right hand side, so let's write that down. The right hand side sum, which is simply equal to this aj plus 1, aj plus 1, plus ak plus 1 over all the diagonals, is simply equal to, we decided that this thing will count each edge, and we can split this into 2 and so on. So each edge n minus 3 times, and because we are summing across all these edges, n minus 3 times the perimeter, sorry for that. And finally, we are ready to combine these pieces. So the left hand side, so the summation of the left hand side was 2d. Let's write that down. And that's definitely, so therefore, that's definitely greater than, strictly greater than the summation of the right hand side, which we established is n minus 3 times p. So therefore, we have found a formula relating the sum of the diagonals to the perimeter of the of this n-gon, convex n-gon. But then we can rearrange it nicely to write it in this convenient form. So we can simply divide both sides by p. These will cancel out. So therefore, yeah, we have the left hand, the first inequality now. 2d over p is strictly, or let's do it the other way around. So n minus 3 is strictly less than 2d over p. Now that's awesome. All right, now the second part. For the second part, again, we will have a combinatorial argument. This one is slightly, we should be careful on that one. And that's why I'm considering to make it into a casework. Before I go into that casework, I want to remind you that okay, so if you have an n-gon, let's say you have this following n-gon, I don't know, maybe something like this. Okay, let's consider this simple n-gon. Okay, there you go. And consider any given diagonal of that n-gon. So we have all these vertices of this n-gon. Let's call this one a sub I, this one is a sub j. So what I claim is that using triangle inequality again, a sub I, a sub j is strictly less than two things. It's strictly less than the sum of these edges, or has strictly less than the sum of these ones. So the lower hemisphere, or lower whatever, the lower region, let's say, is simply equal to ai, a sub I plus 1, this length, the edge length here, a sub I plus 1, and so on. A sub I plus 1, a sub I plus 2, and finally, all the way up to here, this one is a sub j minus 1. a sub j minus 1 a sub j. But it is also possible to express the same thing is still less than the other way around. So a sub j plus 1, a sub j plus 1, and blah blah blah. So you guys already know what's gonna happen. A sub I minus 1, a sub I. Okay, so this, I wanted to remind you of this quick fact, and now let's begin. So the casework that I was mentioning was, the first case is if n is odd. So let's write n as such. So n is odd, n odd. What we will do is, like in the first inequality, once we had this critical inequality claim proven, all we did, we summed over all potential diagonals, which we know the number, which we calculated the number to be like this. So therefore, I'll do exactly the same thing, except that this time when I sum all these expressions on the left and on the right, I have a problem. So which one of these two inequalities, sets of inequalities, should I use? Well, I claim that we should be using the one which have less terms on the right hand side. So for this particular example, for instance, this side has only 1, 2, 3, 4, versus the other part has 6. So therefore I should really use this part. But it will change, right? So I will do summation over all. So I'm basically giving an orientation to each diagonal in that sense. Does that make sense? So therefore, when I sum across all ai, aj, right, for all ij, where you get the diagonal. So I don't want I and j to be consecutive. I is not equal to j plus minus 1. Does that make sense? In mod n. Or mod n minus 1 probably, I should say. Well, okay. So this sum is on the left hand side, and I'm adding across, you know how many diagonals we have. Let me remind you of the number of diagonals was 1/2 n times n minus 3. So when I add across all these, what would just happen? Yes, well, I mean, it is kind of obvious that the left hand side, so this expression on the left hand, would be equal to d, no doubt about that. You are just summing all the diagonals without repetition. But on the right hand side, we are summing either using the first or the second, doesn't matter, the one with fewer terms, less terms. We are summing side lengths, right? But how many times is each side counted, right? So that depends on k, right? Let me give you a quick example. For instance, let's start with an easy case, and then I'll give you a harder case. Okay, consider the pentagon, a convex pentagon, not necessarily regular. For that pentagon, n is equal to 5, meaning k is simply equal to 2. Okay. Actually, let me do it the other way. So let me do it with a minus sign. Okay, I want k to start from 1 at least. Okay, good. Yes, meaning k is really 3 in that case. Okay, all right. Doesn't matter, but yeah, it's I already computed these numbers with where this one is a minus. Okay, so let me rewrite this. Okay, well, what do? We just check the diagonals. It turns out pentagon is a special case where all the diagonals span 2 edges in a sense. For instance, if you focus on say this diagonal, you just realize that the shorter region, which is this, is spanning through 2 edges. So therefore, when I add across all these diagonals, so for each diagonal here, these 2 edges will appear. Each one will appear. But then when I add this diagonal, these 2 will appear on the right hand side, and so on. So therefore, each edge will be repeated 2 times. Because each edge is repeated 2 times, and you are adding all these edges, the perimeter will be twice as much, right? And that thing will be therefore less than 2p. Well, it's just a matter of confirmation now to establish that indeed our formula holds. For instance, let's check if the formula, the right hand side and the second inequality holds in that case. So we have established that that d, I believe, is strictly less than d is strictly less than 2p. Let's see if it works in the case of a pentagon. D is less than 2p. Okay, let's see if this works. Okay, if these two expressions are equivalent in that sense, I can move that p to the left hand side again, so that would be a p here. Okay, so that's what we need to show. Now, noticing that n is equal to 2k minus 1, I should say. So 2k minus 1 over 2, and we're taking the floor of that. That's simply equal to, if it was 2k, and over 2 would have given us a k, so the floor would be k. 2k minus 1, divide by 2, take the floor. That should be k minus 1. Does that make sense? So this first guy is k minus 1. Well, the same thing here. So 2k minus 1 plus 1 is just 2k. Divide by 2 is k. So this one will come out as a k, and we still have a minus 2 here. So therefore, the answer would have been k minus 1 times k minus 2. And sure, indeed, k is 3. So 3 minus 1 is 2 times 3 is 2 times 3 is 6. 6 minus 2 is 4. And that's it. So therefore, our thing reduces to 2p over 2d over p is strictly less than 4. But indeed, that shows that it works. Let's try one more time, because this shape was too symmetric. How about n is equal to 7? Let's do, maybe I can do it over here and everybody would be convinced. N is equal to 7. K in that case would be because it's just 2 times 4 minus 1, so k is equal to 4. Let me kind of roughly draw it. A 7 gone, right? Okay, now do you agree that we have two types of diagonals in that shape? Those that span two different legs, and those that span 3 different legs, 1, 2, 3. Does that make sense? If I go further, it's also the one that spans 3 again, because I'm just looking into the shorter one, right? So therefore, each side is repeated 1, 2 times under this diagonal when we keep adding the right hand sides, and then these diagonals 1, 2, 3 times. So each side is added 3 times. For again on the right hand side. So for each diagonal you keep adding each side 2 times, and then each side 3 times, right? Because it will keep shifting and shifting. For instance, just to give you an example, this guy later on will become this guy, and then finally it will become something like this. For example, if you focus on this edge, you just realize that this edge has been added once under here, twice, and then 3 times. So 3 times. Does that make sense? So therefore, so 2 plus 3, each edge is counted 5 times. So therefore, our formula becomes, and the left hand side doesn't matter. When you add all these diagonals across all the potential diagonals, that will give us d on the left hand side, the sum of the diagonals, right? So therefore we still have d d is strictly less than, we decided 2 plus 3, right? So 2 plus 3p, which is 5p. And again, you can just plug it into to the given, and you just realize that this thing is confirmed. Now we are ready to generalize the odd case. In the odd case, we have diagonals of length 2, which will span 2 edges, 3 edges, all the way up to k minus 1 edges. So each of these sides will be repeated as many times. So 2 plus 3 plus k minus 1 times, which is just k minus 1. We're just adding these. So k minus 1 times k over 2, except that the plus 1 is missing, so I need to subtract 1 now. So therefore, adding all these inequalities on the left, like we did so many times, so the left hand side, so therefore the left hand side is d, versus the right hand side, each side is added how many times? So we decided that each side is added this many times, so therefore this, when you add so many times, first of all, if you added every single one of them one time, each edge one time, we should have gotten the perimeter. But because we are adding each of them so many times, we just need to multiply it with this figure, which simplifies as k squared minus k minus 2 over 2, right? So therefore, I can get a, yeah, so this is just p over 2 times, yeah, I can do it, right, okay, so when I factor out the 2, so this one is 2 over 2, so that will give me k squared minus k minus 2, right? So k squared minus k minus 2, all, well, division by 2 is already done here, so this is here, so this is just k squared minus k minus 2, sorry for that. And further, now the tricky part, I can yeah, I can write this as yeah, by replacing k with n, now we can replace, so k is just equal to n plus 1 over 2, so therefore this whole thing becomes n plus 1 over 2 square minus n plus 1 over 2 minus 2. And you can I guess you can just simplify stuff. Yeah, let me okay, let's quickly do it, because all right, so we have n squared plus 2n, let's just write it, n squared plus 2n plus 1 minus n minus 1 minus 4, I would like to say, yes. And this whole, oh, the divisor here is 4, so this is a 4. Let's change this. This one has become an 8. These are both minus, okay, like that. These two would cancel out. We would have p over 8 actually. N squared, so these just vanished. I have n squared minus 9, I guess, right? Right. Now remember that I need to make it look like this. So n over 2, n plus 1 over 2. Okay, let me play with it a little bit. This is not nice. So let's actually add back the, so let's keep the 2 here and let's have the 4 here. So we have p over 2. Okay, so somehow I need to split it into over 2 and right, and then I should still keep the minus 2. Okay, so let's handle the minus 2 first. I want to make sure that there will be a minus 2 here. So this is 9 over 4, 8 over 4. So so therefore I still have a minus 1 over 4. Hey, that's the 4. So it's just a minus 1. So so that gives me the idea. N squared minus 1 is just n plus 1, n minus 1, and boom. And obviously this expression is awesomely cute looking, because you can easily make an argument where these two are actually equal to each other when n is odd, right? So that has been amazing. We have just shown that d is strictly less than this. But by the same token, if n is even, i.e. n is 2k, n is equivalent to 2k, the same thing will happen. We will keep adding these inequalities, whichever is the one which has the lower number of side lengths in it. When you add them, the left hand side will be decidedly d, so d is strictly left hand. Now let's have a look at the right hand sides. So each edge will repeat how many times? Like we did in the previous 2 questions. Consider, let's say, the hexagon, not necessarily regular. It has, oh, wait a second, 1 type, 2 type of diagonals, right? The one which looks like a diameter, and then the shorter one. The shorter one will trace it 1, 2 times. the diameter will do it. Well, for the diameter it doesn't matter which side we pick. So 1, 2, 3 times. Does that make sense? But 1, 2, 3 is just because we are picking the smaller guy, because we are trying to find the smallest upper bound. Right. So therefore, that's just, you can think of it is, it will be definitely, because it's the shorter end, it will be definitely less than p over 2, right? I'm talking about this diagonal and the edges associated with that diagonal, because it's less than half of the thing. Plus, and then each side is counted 2 times. Does that make sense? Let's quickly check the octagon. How do we draw an octagon? Okay, I think I already got one. Hold on. 1, 2, 3, 4, 5, 6, 7, 8. Awesome. So we have those diagonals of length 2, those diagonals of length 3, and then those that look like a diameter, right? And the same reasoning. So p over 2, because we will just pick one region, one half, with the half which is shorter, less than half, plus, and then each edge is counted 2 times under this type of diagonals. Each edge is counted 3 times under this type of diagonals, right? So 2 plus 3 is 5. So it will become like 5p. But then the same ideas will hold. So therefore, when we add across all the diagonals this many times on the right hand side, the left hand side is still d, right? Does that make sense? This is the case where we had a hexagon, the case where we had an octagon, and you can easily extend the argument, and you just realize that our expression would look very similar to this, except that in the even case, because we have this diameter type of diagonals which look like a diameter, we will have this extra additional term, but the rest of the terms are congruent, so which is like we did here in this previous work. That would be just p times, and then I will factor out the 1/2, so it's really p. Oh shoot, we forgot to count the number of diagonals in the first thing. So how many diagonals we have? Because we have n is equal to 2k. How many diagonals which look like a diameter? Sorry, we would have k of them, right? So therefore, I should be careful on this. It is k times p over 2, right? Does that make sense? Because each one we took the portion which is less than for each diameter looking diagonals, and we took the one with sides summing up less than the other side, and those sums, they add up to be less than half of the perimeter. Okay, so it's been crazy here. So therefore, so let's just get, oops, what happened? And like I said, the second part, oh sorry, this part won't change. So it is p times, or you can, if you will, we can factor out the 2 as usual, and it will become and then it will become k times k minus 1, all divided by 2 minus 2 over 2. Oh sorry, the division by 2, we already took it out, so just minus 2. That's it. And when you extend it, it will become well, the final product. I'm writing the final outcome, minus 2, and now replacing the k with n over 2, I should say, p over 2, n over 2 times n over 2, right? So n squared over 4, n over 2 times n over 2 minus 2. But now I want to replace these expressions with the floor. That's easy, or like my son says, easy peasy cheesy or something. N over 2, that's the same thing, right? And because n is even, and then even this one is the same thing, minus 2, and boom, we have exactly, for both solutions, we have exactly the right hand side format, right? So oh my god, I really messed it up on this side, right? Does that make sense? So therefore, the right hand side is where the action takes place. The left hand side was pretty standard. It was quite easy actually, but on the right hand side we do careful casework. The whole idea is to intelligently use the triangle inequality and add up across all the diagonals in a careful way and follow up how many times you are counting each, over counting each side and each diagonal. So the triangle inequality, I should say here. Okay, so that solves this problem. Hope you enjoyed it and looking forward to see you guys in our next lecture.